Hi everyone, Mary here, and this time we're going to talk quite a bit in this video about specific heat, and we're going to start with the quantity of heat energy equation. In this equation, Q is mc delta T, where Q stands for quantity of heat energy. Now that is going to be measured typically most of the time, that's going to be in joules, and M of course is mass. Delta T is change in temperature, and that can either be in Kelvin or degrees Celsius because it is change in, and these two are the same size. It doesn't matter which we're using. And the third thing in this equation is something called specific heat. We're going to spend a lot of time discussing that in a minute. When do you use this equation? It's useful if you want to calculate the heat needed to raise or lower the temperature of a substance. So, specific heat. You woke up this morning with some sort of a gut instinct about specific heat. And to help get your head in the game, let's talk about pizza. If you have a hot, wonderful pizza that just comes out of the oven, my question is, which part of the pizza burns your mouth? Is it going to be the cheese, the toppings, the sauce, or the crust? And we've all probably had too hot pizza sometime in our lifetime, but there is one part of the pizza that is much more guilty of mouth burns than the other parts. And that all has to do with specific heat. And we'll talk about this again at the end. Now, the definition of specific heat is this. It's the energy needed to increase the temperature of 1 kilogram of a substance by 1 degree Celsius. The idea is that different materials heat up at different rates. Things like mercury, gold, lead, metals have very, very low specific heats. One of my favorite examples of this is if you're ever wearing a necklace and you're blow drying your hair. If you blow dry your hair and you've got a necklace on, I quickly learned in my life not to do that because my necklace would get like hot, really, really hot. And it was like, don't do that. Because of this low specific heat, they absorbed the heat so quickly that my neck got hot. Some things like water, methyl alcohol, steam, benzene, these things have big specific heat. That means that they heat up slowly, but they also mean they cool down very, very slowly. Now, why do I have a pan of lasagna sitting here? Great example of specific heat. Very often I've seen people take a pan of lasagna out of the oven. It was just in the oven at, let's say, 350 degrees Fahrenheit. And they use their little hot pads to take the lasagna out. They put it on the counter. And then with their naked little fingers, they take their hot pads off, and with their naked little fingers, they peel back the aluminum foil, of course being careful not to get hit by the steam. That's specific heat. We all know that the aluminum is going to cool down so quickly, we're going to be able to touch it soon, but the steam and the stuff coming off of that lasagna is dangerous hot, like it could burn your skin hot. Now, there are multiple categories of things that have different specific heats, and metals is one. Metals tend to have very low specific heats, meaning they heat up quickly and they cool down quickly, like that aluminum foil, like the necklace with your blow dryer. Anything that's metal is really useful if we want to cool something down. It's useful for something called a heat sink. If you have a lot of heat in a central processing unit or in a computer or in some sort of a machine or an engine, or you've got an air conditioning unit and you want the heat to dissipate, you make the exterior of it metal and you give it lots and lots of fins and surface area so there's a lot of airflow and the heat will just go away very, very quickly. We use metal pots for cooking because if you were going to fry an egg directly on the fire of your stove, that would be just messy. So you put the egg inside the frying pan so that the heat will go through the pan and into the egg. But the metal is just really good at transferring heat. Non-metallic things tend to have high specific heats. They're very good thermal insulators, and we use them when we want to prevent heat from moving. Things like fiberglass, sprayed foam, pink foam, lofty things like goose down, polar fleece, wool, These have lots of air pockets, and air is mostly oxygen and nitrogen. So air gaps, like thermal pane windows, do not allow heat to go from one side to the other. Those non-metallic things like air will prevent the heat from flowing. If you remember from when you had chemistry long ago and far away, you've got the nonmetals on the right-hand side of the periodic table, and these nonmetals are really great insulators. And they make things like styrofoam, which are carbon and hydrogen compounds, and spray foam, which are carbon and hydrogen. Polar fleece, carbon and hydrogen, all these non-metallic things. Fiberglass is silicon dioxide. Silicon is here, oxygen is here, non-metallic stuff, great insulators. Now the purple things on the left side of the periodic table, these are our metals. Metals tend to have low specific heats, and they heat up quickly and they cool down quickly. Water has a crazy high specific heat. For the chart that I showed you earlier, water has the highest specific heat on the chart, over 4,000 joules per kilogram degree Celsius. And the vast majority of planet Earth is covered in water, and that has a huge effect on things like cooling and climate. So we use water because of this high specific heat for cooling systems. For example, you perspire. When your body gets warm, your body has to get rid of or dissipate that heat. And so when you have water evaporating off of your skin, it removes heat from your system. That's one of the reasons why athletes must stay hydrated. If they don't stay hydrated, the water can't evaporate and their body will overheat, and that will cause all sorts of internal problems. We use water in radiators in automobiles because it's so fabulous at removing heat from those hot internal combustion engines. Radiant heat in homes contains pipes full of water. They hold heat very, very, very well. They're really slow to heat up, but boy, once they're warm, they're toasty warm for a long, long time. If you ever pass a power plant that makes electricity, very often you're going to see cooling towers, and cooling towers are literally contained buildings where they make it rain. Very often electrical power plants are next to some sort of a river and stream, and they use some of that water to cool down the engines, but they have to put cold water back into the rivers and streams, something that is normal temperature for that river. So how do they cool it down? They pump the water to the top of a cooling tower. And what's going on in here? It's literally just raining. And as that water falls, it cools. What you're seeing out the top is just steam. Those are nothing but clouds. And the whole purpose is to cool the water before it goes back into the river. But why do we bother? Because water has this high, crazy high specific heat. Appliances that heat water tend to be expensive. They tend to have very high wattages. Things like a water heater, things like a clothes dryer. Both of these appliances have huge, massive wattages, and that means that they are going to be very expensive to operate. If you want to cut your electric bill, cut down on the amount you use both of these, and your electric bills will fall. Now, climate. Water has a massive effect on the climate. I live in the Midwestern part of the United States. I live in the state of Wisconsin, and kind of right on the cusp between hardness zones 3 and 4. Now, who uses hardness zones? This map is used by gardeners trying to determine which plants will survive over the winter. So this gives you an idea of the coldest temperatures in an area. Hardness zone 4, the coldest temperatures they typically get in this light green is about minus 40. This darker green, they can easily, I said minus 40, minus 30. The darker green, they can typically get down to a minus 40 in the winter time. And as you go further north, it gets colder, and as you get further south, it gets warmer. And that makes sense based on solar heating and latitude. But watch what happens when you go to the West Coast. If I take the same latitude and I go to the West Coast, you get, well, here's Washington State, Oregon State. Look at that. Right at the same latitude, we are in hardness zones 8 14-9. So the coldest temperature it's going to get is 10 or 20 degrees Fahrenheit. What's going on? Well, they're right next to the Pacific Ocean. And that ocean has spent all summer absorbing heat from the sun, and all winter it gives that heat back. So it makes the climate on the west coast of the United States very mild, very temperate. The winters will not be as cold. But then, of course, all summer it's giving back that heat, and all winter it doesn't have it's got this cold ocean over here. So it tends to be a little cooler in the summer and a little hotter in the winter. Kind of makes it mild, and we like mild. That's why a lot of people like living on the West Coast. If you go to the East Coast of the United States, it's not exactly the same. If you go to this area, they have hardness zones of about a 6. Now, how can that be? Because they're also next to the ocean, but they're next to the Atlantic. Well, most of the weather in the United States comes from the west to the east due to big, massive jet streams of atmosphere that travel from west to east. So people who live on the Atlantic coast get a lot of their weather from the inlands, and that means they don't get as much heating effect from the oceans as the people who live next to the Pacific. When I went to college for a while in England. And when I went to school in England, I always thought it was fascinating because I was there in the wintertime. And England is about the same latitude as Hudson Bay, way up north in Canada. Very, very cold. Hardness zone up here in the twos for commonly minus 50 degrees in the wintertime. And you've seen probably a lot of British movies. And when I see Harry Potter and Harry and Ron and Hermione are running around, yes, they get a little snow. Yes, they're wearing cute little wool jackets, but they're not freezing. It's not 50 below zero. What's going on? Well, it's an island, and the island is surrounded by water. And so that water is making the climate much more temperate. Here is a hardness zone map of the British Isles. And the very coldest part of the British Isles will have a hardness zone of 8, meaning, yes, it will freeze, but it doesn't get colder than about 10 degrees Fahrenheit. Way down in the south corner of England, down in Cornwall, they have palm trees. And they have palm trees down there because their hardness zone is about a 10, which means it almost never freezes. And it is so warm because of all the ocean water, all the heat from the ocean, that it keeps that from freezing. Ireland is known as the Emerald Isle, and it's a beautiful, beautiful country. And one of the reasons it's so beautifully green is because of the fact it's surrounded totally by ocean, and that keeps it from getting too hot in the summer and too cold in the winter, and things just almost never freeze. Hawaii, similar, middle of the ocean, way up on the tippy tops of some of the mountains in Hawaii. You can sometimes get below freezing, but just barely, once in a blue moon. Vast majority of Hawaii, the 95% of the whole rest of the state, never going to freeze, and most of the state, you're almost never going to get below 50, and it all has to do with that specific heat of water. So let's talk about pizza. What burns your mouth? Is it the cheese, the toppings, the crust, or the sauce? Yeah, it's the sauce. Sauce is made of mostly water, and water has that crazy high specific heat. Now, the cheese and the crust are insulators. They're non-metals. They're good insulators. So the cheese and the crust insulate it like a little blanket, keeping that sauce extra piping hot. And so they're not the culprits, but they do play a role. All right, we will see you next time. Bye-bye.